Hey robot makers, hope you're having a good day so far. So do you want to build a LiDAR powered robot using a Raspberry Pi Pico and the Kitronik motor driver for Pico? Then this is the show for you. So let's dive straight in. My name's Kevin, come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Let's get over to our main notes and we can talk about what this LiDAR robot is all about. I've got it next to me and we'll have a play with it in the demo in a second or two. So yes, this is I'm calling this LidarBot. That's a really creative name, isn't it? It's not the first LiDAR robot I built, actually. The first one I built, this is the latest incarnation of the first robot I built with a LiDAR. This one is a RP LiDAR. It's quite a big unit, takes up the entire top section of this robot here. And these cost about £100, about just under $100, is it? Maybe a bit more, not sure what the exchange rate's like nowadays. Anyway, this is a much smaller LiDAR unit. I'll just grab it off the desk there. You can see this one's tiny. And these are about $25 or thereabouts. So we're going to have a look at how that works today, and we're going to use the Kitronik motor driver board as well to provide the robot with a bit of movement. And it also houses the Raspberry Pi Pico on top. We'll also talk about a bit of troubleshooting. That's a bit of a foreshadowing for today's show. Okay, so let's talk about the design of this. So I started out with my favourite design of robot, which is the BurgerBot. So this BurgerBot robot has these nice little fixed casters, as I call them, rather than the sort of regular casters. I've got a bag of caster wheels here. These kind of caster wheels that you find on trolleys and things. You can just get away if you've got a desktop robot with just little stumps. And this one prints completely flat. I've just put this little rangefinder holder on there, and that's screwed into place on that particular version. But this base is really simple to design and put together and modify. So I modified this one so that it could house a couple of additional parts, such as this little LiDAR holder. So the original LiDAR, the LD06, comes with a little Raspberry Pi mounting bracket, and it has these two kind of studs. If I hold that up close to the camera, you might be able to see there. There's these two studs, and they have these little like rectangular pieces as well, and they have a hole in the top, and there's a little plastic screws into there, kind of like a wood screw. And this one is a piece I designed. The idea of this will go on the very front of the BurgerBot, and there's some holes that allow that to sort of attach into place. So it means the LiDAR can slot into place and then be screwed solidly so that it doesn't move around. So that's the very first piece. There's a couple of extra holes as well at the back for the motor driver board, and I'm going to have a custom piece for that too. So there you go, there's the LiDAR holder, as I call it, with the screw mounts. You can even put the capture nuts in place there, captive nuts, so that it really locks into place. And it's slightly lifted above as well, so that the LiDAR, the actual sensor, is slightly proud of the wheels. So if I hold up the finished article, you can see there that the LiDAR unit just slightly past the tops of the wheels there. And then the last piece at the back there is the motor driver holder board for the Kitronik Pico motor driver. Really like this board. It's very, very affordable, and it allows you to slot into place a Raspberry Pi Pico or a Pico 2 or a Pico 2W or a Pico WH, whatever kind of Pico that you actually have there. I've tested this on a number of different Raspberry Pi Picos as well. As long as it's got the header pins on, it just slots into place nicely there. And that one's also raised up slightly. There's three little sort of lug things that stand up because the board has some solder points underneath, and it just raises them above so that it screws in and stays nice and flush on the top there. So that's all we really need for the kind of electronics parts, and we just need some motor holders for the N20 motors. I use the 150 RPM version, and they're really nice and simple to use. Just solder a piece of wire, like a black and red wire to them, plus and minus, and you can then control that by connecting it up to the terminals on the motor driver board. I've also used some of my favourite wheels, which are the Moon Buggy wheels from Pimroni. These ones you can sort of just pull off as well. They have a nice little connector, so you can push them straight onto those N20 motors, and yeah, they're quite affordable as well. They've got a nice little grip on them, and they work great on the sort of desktop environment. So there you go, there's the finished article there. So we've got the LiDAR up front, we've got the Pico at the back on top of the Kitronik motor driver board, and everything's sort of connected together with just little wires and cables. I think I've actually used some regular jumper cables for this. Let's see if I've got any spare. One just there. What I mean by jumper cables is these kinds of cables like so. So they just have those little connectors on the end, and you can literally put that into the screw terminal, screw it into place, and you can then put that into whatever else it needs to connect up to. So the LiDAR unit itself doesn't have like a USB like the larger brother one that it has there. It just has this little DuPont type connector, and you just push into place the pins. We'll talk about the pins next. So wiring this thing up is quite straightforward to wire this up using the Kitronik Pico motor driver board, and this isn't sponsored. This is one I bought with my own money because they're very, very affordable. But I think Kitronik's a UK-based company as well. They do a lot of good stuff for Pico and Microbit. So a big fan of Kitronik, and they do a lot of stuff for Microbit as well. So this one has the terminal block on the top, so you can put between 3 and 10 volts in the terminal block there. So 9-volt battery is fine for that, or if you've got any of these kinds of battery boxes, you can plug those in as well. It also has a power switch. You can turn that power on and off, which is often missed on robotics boards. So I really like that they have that. And next to the terminal block at the top there's also these little pins. So you've got plus in the middle and minus the ground on either side of that. So you can pull that to power the LiDAR, for example. And then on the right hand side over here, we've got a whole bunch of terminal blocks that do various different things. So these first four, each of these two represent a motor. So we have motor 1 and motor 2. And we can simply just connect up the pins from that brushless DC motor into there, and away we go. The next four are GPIO pins. So there's 4 GPIO pins kind of in 2 pairs. So there's GP0, GP1, GP26 and GP27. I'm not sure why they're ordered in that particular way, but that's the way that they are on the board. And then we also have a breakout for 3 volts and for ground as well via the terminal blocks. So we're going to connect up GP1, which is this one here, to our LiDAR. So the LiDAR unit, I'll show you the LiDAR unit wiring in a second. It's very, very straightforward, just one pin. So yeah, this Kitronik's motor driver board, the Pico motor driver board as they call it, very, very affordable. It's about £10, $10-ish to purchase. Works with all Raspberry Pi Pico form factors, and that means that it's really easy to get up and running with this for very, very low cost. I think Raspberry Pi Pico, the original one's about $4, something like that. It's very, very cheap. And then depending on the sort of larger models like the Pico 2, the Pico W, WH and Pico 2WH, the price kind of goes up a little bit from there. So we're going to use the 2 motors. We're going to use motor 1 and motor 2 on our particular project, so this is ideal for this. The external power pins are also ideal for powering our robot, so the motors need a lot more power than that 3 volts that you get from the Pico, and that the Pico needs to work. So ideal for powering the motors there. The on-off switch is great for turning the robot off when you finish playing with it. And the 4 GPIO pins, the way that they're broken out with those terminal blocks makes it really easy to sort of use this on another project. So you're not kind of locked in, soldered in to this particular project build. And we've also got 3 mounting holes as well. So I've used those to secure the board in place on our particular robot. And I think this is overall very great value, great quality, really great build, and very robustly put together. Very, very easy. There's also some great documentation on the website that tells you all about how to use this with some example code. We'll be using some of that in a moment. So back over to the LiDAR. So this is the LD06. I think this is made by LidarBot. I think this is the name of the company that produced this one. Where is it? It says LidarBot on the side there. And the LD06 I think is still available. It's about £25 to buy, and yeah, very, very affordable way of getting LiDAR into your robots. So this has 3 pins. There's actually 4 pins on the back, and there's a little connect that goes into the side there. And you can see we have 5 volts and ground, so we do need 5 volts, which makes it a little bit awkward given that the Pico runs on 3.3, but we can get an external power supply in on this particular thing. And then the receive and transmit, the transmit isn't used, so the LiDAR unit doesn't actually kind of transmit anything it doesn't receive anything in, I should say. It just sends data out. So we actually have the RX pin on the Pico receiving that. So we're going to use something called UART, which is a oh, I can't remember what the actual acronym stands for. I'm going to grab my little Google and find what that stands for, because I always forget. Universal Asynchronous Receiver Transmit, and it's a way of transmitting data over different components. So we're going to be using UART to connect to this, but we only need that one half just to get the data from the LiDAR. We can't send any data to it, and that's a bit of a awkward thing, because it means we can't send a kind of a reset. We can't tell it to give us information. It will just keep spitting out information. We just have to keep up with that. Now, a word of warning with this, to get a bit of foreshadowing to what I'm going to tell you in a minute. So the colouring of the pins may not be what you expect. So on the actual unit I've got here, if I go to the overhead camera for a second, I'll show you the wiring on there. You can see there's a blue cable and a red cable. So the blue cable is on the very outer edge, and then the second one in is the red cable. Now, universally, red means 5 volts. Not in this case. So in this case, the blue is 5 volts and the black is, the blue is 5 volts and the red is ground. So I wired this incorrectly for about 5 minutes on my particular LiDAR unit, and we'll see how that works out in a minute or two when we actually come to test this. So I'll see what the results of that is. The only way I found this out was because when I touched the Pico that was sat in the Kitronik board, it was absolutely red hot. The actual chips were too hot to actually touch, so I removed the power immediately and then let everything cool down and came back to it. But yeah, you can see on the overhead there, it is actually working. There is the thing is spinning around. We'll actually open this up in a second and show you what it looks like inside, just so you can see what a LiDAR unit looks like inside as it's spinning around. So yeah, just be warned, always check the spec sheets for these. And there are lots of different versions of the LD06 typically, so there's clones of it and so on, but yeah, check the pins. So if you like what I do, if you want me to make more of these kinds of robot type videos, then definitely drop me a like on this video. I always appreciate likes. I'm kind of in it for the likes and subs. Don't make very much money doing this, if I'm honest. If you want to drop me a comment as well, let me know if you have a LiDAR unit and which one you use. And also, if you've not subscribed to the channel, please subscribe. It means so much for me. We just passed 40,000 subscribers this week, so really, really pleased about that. That's a very big milestone. Hopefully we'll get up to the 50,000 this year as well by the end of the year. I do go live every single Sunday around 7 o'clock British summer time, so definitely check out and hang out if you can. If you're watching this on replay, 7 o'clock Sundays, they're the times to catch me. Okay. So let's have a bit of a demo, shall we? So first of all, let me just grab over to me for a second and I shall load up Thonny, and I'm going to then share with you some test programs. So let me just bring up the very first one. Just going to bring that over there, and then what I shall try and do is get the camera on here and also Thonny on the other part of the screen so we can see everything at the same time. So Kitronik provide a nice little library. If I load up this Pico motor driver, this is a library that they've created, which makes working with the board that they've created real easy. As you can see there's the Kitronik board itself. Got Raspberry Pi. I think this is a Pico WH. So it's not a Pico 2. It has got the Wi-Fi chip on it, and it has got the header pins already soldered into place. So that's the WH variant of that. And you can see there I've got a couple of different things wired in. I've got an external power supply. If I go to, let's see, that camera, is it? You can see I've got external power supply kind of wired in here, just providing power into that little block there, just so that I can guarantee that this is running on 5 volts. You can just about see there that the LiDAR is spinning round and detecting things at the moment. So we'll get to that in a second. So this Kitronik's Pico motor driver board. So you can see that they've got pin 4 and 5 for motor 1, pin 9 and 10 for motor 2. Forward is pin 5 or pin 9 driven high with a P4 or P10 held low. Reverse is kind of the opposite of that. And they've got these motor on with a motor number, a direction and a speed. And if the speed is 0, then It's not really going to do very much. Otherwise, if the speed is greater than 100, it's going to set that to 100. So this is just kind of a bit of error checking. If it's less than 0, set it to 0. If it's greater than 100, set it to 100. And then they've got this pulse width modulation. So this is going to be speed times 655.35. So whatever this speed is, it's going to multiply it up. So 65,305, if you're aware, is 2 bytes. So essentially, pulse width modulation just needs 2 bytes worth of information to delineate the speed. If motor is equal to 1, then, and if the direction is F, which means forward, then we can drive the motor forwards. You can see there, self motor 1 forwards.duty, unsigned 16-bit integer, pulse width modulation, and then the other one is set to 0, and then the reverse duty is set to 0, and then you can see there, otherwise if it's reverse, it kind of flips that over. Otherwise, if it's not F or R, then it just says raise an exception, invalid direction. As, well, at least you'll know. And then otherwise, if it's not motor 2, the direction is a forward, then you can see the same thing again. Otherwise, if it's none of those, then it's an invalid motor. So if you pass motor 3 or any other number than 1 and 2, you're going to get that. And then motor off simply just sets whichever motor you pass in there, the speed to 0, so it stops the motor. You can actually use stepper motors on this, but you actually have to use all 4 of the pins to drive the stepper motor. We're not going to be looking at that today, but you can kind of see that that's included in there as well as the step angle. So that's the driver, the Pico motor driver. We've got that installed on our Pico. You can see there the Pico's file system has that Pico motor driver there. And we're going to look at this test motor. So this is some very simple code. So from Pico motor driver, import Kitronik Pico motor, which is the class that represents their driver board. We're also going to import time and sleep, and we're going to basically just create this driver equals Kitronik Pico motor. We're going to move the robot forwards at 100% speed, and we're going to do that on both motors 1 and 2. And then it's going to sleep for 2 seconds, and then it's going to turn off both the motors, and then wait for a second, and then stop. So very, very simple. So what I'm going to do, I'm going to zoom this camera back a little bit, because this is probably going to shoot forward quite rapidly, I expect. So let me just grab that and then click on run. So you can see there, quite happily runs forward. It's being pulled slightly to the right there, because I've got this USB cable connected up there. So we could even set that to, instead of being 2 seconds, we could have that as like half a second. Let's try that instead. And that should be a little bit less. There you go. Works fine. Nice and powerful. I think I've got this currently set at 5.4 volts and it's 0.2 amps of power. I think that's right. That it currently draws. If I just hold that up and then press forwards. Yeah, it uses about 0.4, half an amp, is that right? That sounds like a lot of power, but that's what the power supply says on it there. Okay, so that's the testing the motors. We could do a lot more work with this if we wanted to, but it just so happens that I created a BurgerBot, which has all that kind of logic in it previously. So if we open up BurgerBot, what I do need to do on here is basically change the pinouts so that they are the same pinouts for the board that we're using. But because we've got BurgerBot, that also means we can use the gamepad. So if I load up my test gamepad code, this brings in the gamepad, and I have the gamepad over here. So if I click on run on this one, let's just run that and see what it says down there. So it says found Kev's robots, and on here it now says connected. If I hold that up to the camera there, you should be able to see that it says connected. It'll just take a second. There you go, connected. And if I hit some of the buttons on here, we should be able to get the robot to move about. So I've not quite got the pinouts right on this one, I think, because it's just using one of the motors at the moment, which is the left one there. But basically that works fine with me just pressing this button here. So as I press that button there, let's try that one, let's try that, and then let's try forward. So that works fine. We can connect using the gamepad 2, which is basically just Pico powered. You can see there we've got the Raspberry Pi Pico, and I've got a little screen on there just so I can see what commands I'm actually pressing there. So as I press that button there, you can see the robot's kind of spinning round to the left, like so. So the Kitronik board works fine with the gamepad, which is great, so we can leave that there. Let's just stop that code from running. And then let's get to the bit that we're really interested in, which is the LiDAR. So gone through those there. So what I'm going to do, I'm going to load up LiDAR 3, which is some code I've got here. I'm going to talk you through how this works, and then we're going to see what happens. So I'm going to import the UART and the pin, because we need to interface with that one pin to get the received data from our LiDAR. I'm going to import time and math. We do quite a bit of math in here. And then we're going to set up that UART. So this UART, which is that universal asynchronous receive transmitter. It just checks the other screen. It's got a really fast baud rate. Normally you see like 9600 typically with devices. This is 2300, 400. So 230,400 baud, which is really fast. There's a lot of data coming out of that LiDAR sensor. And we have two pins. We have the transmit pin on pin 0 and the receive pin on pin 1. This is really the one that we're interested in. And we have to set the ID on Raspberry Pi Picos. UARTs are paired up with pairs of pins. So if you try and put pin 1 on the transmit and pin 0 on the receive, it'll basically say that's a bad pin, bad combination. We've got this flush UART. So the UART is a buffer. And if we put data into that buffer, when we come to use that buffer, if there's data that's already there, it can get confused. So we want to basically just read anything from that buffer. And this is what this, if there's any data in the UART, then just read in 32 bytes at a time, whatever's in there, and basically just throw that data away. So we're going to do that until that buffer is empty. Once we've flushed that, so that's where we actually use that flush function, we can then set up some things. So what I wanted to do on this robot, and this is running on a Raspberry Pi Pico in Thonny, I wanted to create a radar. So I want to sweep round and see what objects we can see sweeping around our radar screen. So the screen size is going to be 21 characters wide and tall. The center of the screen is therefore going to be half of that. Double slashes basically just mean divide and throw away any of the decimal points. We just want an integer, a whole number. The maximum radar is basically the center -2, so we want to leave room for a border. And then the distance threshold, this is how far do we want to be able to detect with our LiDAR and throw away the data. So these work for about 12 meters or something. They're a ridiculously large range for the small unit that it has. These are actually used quite a lot in robotic vacuum cleaners as well. So you may have seen these popularized there. So this creating radar function is basically going to create like an array, and it's going to fill that array with points that we find from our radar scan, from our LiDAR. So this piece of logic here with these two loops, so y and x, it's basically going to plot some points based on the distance of the object that we find on there. So this distance, math square root dx times dx plus dy times dy, helps us figure out where things are in that space. And the maximum radius minus half is less than distance, is less than the maximum radius, then we plus 0.5. This is a way basically just drawing that circle and putting the points within it. We're also going to draw some markers. So the very center will have a circle, and we'll also have some pipes, some sort of straight lines and horizontal and vertical lines is what I'm trying to say there. And in the very center, sorry, it'll be the little plus there, and that will return the radar plot. We then want to plot points on our radar array, and this is what will happen. So if the distance is greater than the distance threshold, basically just throw away that plot point. We don't want to plot that, and it's beyond our distance threshold, and that's a tunable constant, so we can change that at the top of our code if we want to make that, say, 6 meters. I've got it as 1 meter at the moment, so 1000 millimeters. Where are we? So if the point is within our distance threshold, then the radius is going to be an integer, and it's going to be the distance minus the distance threshold times the maximum radius. We could have done a double slash there, to be honest, but we've not done. We've just cast it into an integer. And then if the radius is greater than the maximum radius, the radius equals the maximum radius, so it just keeps it within there. The angle radians, so a lot of the data that you get out of these LiDARs can be in radians rather than angles, so we just need to multiply that out to get the answer that we need, and we're basically just going to plot the x and y, just doing that little bit of math there for cosine and sin. And yeah, if 0 is less than x, basically this is just checking, is it within our plot point? Otherwise, throw it away. If not, just draw this little dot, and that will appear on our radar screen. We're then going to print our radar. Now this thing here is quite interesting. On Thonny, this should clear the screen. It should basically just scroll the screen up, and it'll keep scrolling the screen up every time it redraws the radar. And it should give the illusion that our radar is kind of, you know, drawing itself out, even though it's just a console, a text console. And then for each row in our radar, it's basically going to join the rows together and just draw that out. So mainstream reader. So this bit here, we've got some variables we need to set up. So the radar is going to be create radar. The current angle, so we're going to be sweeping round on our LiDAR. So what is the current angle? That's going to be stored there. Packet started, so there is a very specific number that we need to look for. I think it's 52 hex, and that tells us this is the start of a whole packet of data from our LiDAR. So at this point, I'm just going to show you where we find this kind of information out. So if I go over to here, this is the kind of spec sheet from the manufacturer of this. So LD06 Lidar, principal, it's a time of flight laser, product. Very, very small size, low cost, highly reliable, long working life. There we go. Development manual 1.0. So we're interested in this kind of packet format, which is on page 4. So I'm just going to scroll past, show you this. There's a lot of guff there about what it is all about. You can see there, if this little robot is in this room, this is the data that we should get from those plot points. So there's the pinouts. So pin 1 is the TX that's transmitting from the radar. The radar output is going to be 3.3 volts, which is nice and friendly for our microcontroller. Pin 2 isn't actually used. That's the motor control signal. We don't actually use that one at all. Number 3 is ground, and then number 4 is our 5 volts. So minimum is 4.5. But 5.5 is what we get away with, which is kind of just, I'm on 5.4 volts on my power supply there. And there we go. So then you can see the baud rate is this 230,400 baud rate. We've got 8 data bits, 1 stop bit, no parity check bits, and no flow control. If you've ever set up UART, that's kind of a very standard kind of setup, the 8100 thing. Now the data packet format, this is something that we need to encode within our program. So we need to look for this 54 hex. There's then a data length byte. There's then the radar speed with the least significant bit, most significant bit. The start angle, so where are we actually starting from? The actual data itself that's coming through, which is about the distance and so on. And the end angle, the timestamp, and then there's like a cyclic redundancy check byte as well. So we need to be able to store that in something. This is like a C example here, but there's the data structure for the data that we'll be reading in. And there's a typical kind of a block of data that comes from the LiDAR. So that's all in C with its squiggly brackets, but they're giving quite a lot of information there. You can also see within each data packet, and we should get 12 data packets, I think it is, from our LiDAR. So we've got a distance value, so how far is the object from our laser. How confident are we that that is correct? And that's interesting that it can give us that confident byte. It then does the same for the measured 0.2 and then so on. So it's the same kind of thing, a distance value, a confidence value, and then we then move on to the next points. So the lower the intensity, the smaller the confidence is. So if not very much light has come back, it's not really confident that there's actually something there. It could just be reflection or refraction rather, reflection. For a white object that's 6 millimeters, typical confidence is around 200. So we can filter out using that confidence level stuff that isn't actually there, that could just be noise or could be studio lights or whatever. So that's how we basically use that information. Again, it's got typical kind of values in there. So distance value E0, this is in hex, so that's 224 millimeters, and then the confidence is 228. You can see the next one, 222 millimeters, confidence is 226. They're pretty strong confidence values that something is there. And then there's our LiDAR unit. It has this little triangle on the top there, which tells you that that's forward. That's the sort of 0 point, going all the way around back to 360 and then back to 0. And it'll take a number of different readings, each with a packet with the distance and the confidence for each of those. So it'll measure out the thing that it's bounced back off. That's the D, the distance, and the confidence is just how much light has actually been returned to the sensor. So there we go, and it's even got some ROS instructions on there as well about how to go about setting that up. So let's go back to our code and see what we've got in here. So we're going to read a byte of data. We need a little function to do that. So while not UART any, so while there's no data in there, basically just wait for a thousandth of a second. Otherwise, read 1 byte of data. We're going to read 1 byte at a time and then process each byte. We can then print waiting for packet that's in between those functions. And then we've got this while true, so it's going to run this code forever. So it's going to read a byte in, and then if we've not started the, we need to wait for this packet started byte, which is that hex 54. So this B is like, this is binary data, and then /x I think means it's in like a hexadecimal format. So 54 is the value that we're looking for as the starting special character. Once we've read in that, we can then read in the second byte. If the second byte is x2, oh, sorry, 2c, that's the other piece of information that we need. That actually is just the version of the LiDAR firmware. We can then find that we've got the header, so the length is basically reading in that byte, the height is reading in that byte, the packet length, the starting angles, the ending angles, the timestamps, and so on. So once we've read in all that information, we can then process that packet of data. Otherwise, if we want to read in, so that's basically the header information, the next pieces are then going to be the actual data we want. So we're going to point our buffer plus a byte, so this is so that we can record which bytes we've processed and where they're going to be on our radar. If the length of the pointer buffer is greater than or equal to 3, then we want, that's basically it. We've thrown away those 2 first bytes for the starting one and the version number. We can then check the distance. So we're going to read in that it's either going to be a pointer buffer to 0 or a pointer buffer to 0 shifted by 8. We can then read in that confidence value as well, and that's going to be in the pointer buffer, the sort of second element of that. If the points are greater than 1, then we can basically interpret the angle. So the starting angle plus the ending angle minus the starting angle times by the points. And if I just move that up a little bit there, you can see divided by points expected minus 1. Otherwise, interpret the angle is going to be the start angle. And if the interpreted angle is greater than 360, that really shouldn't happen. Then we just set it to be minus 360, set it back to 0. Plot point, radar, interpret angle and distance. This is going to plot the point on our radar. And the last bit's there. When the last point is parsed, basically just reset so that we're not actually waiting for a start packet at that point. That's basically going to look like this. So let me just bring up this here. Let me make sure we're nice and centered. Sorry about that. And let's run our code. There we go. So let's wait for that to start. Make sure everything's good on there. I'm just going to check on the screen as well. There we go. So we can see that there's some data coming through here. We've got this kind of line and then there's like random splats of data there, and the robot isn't moving, so that doesn't look right. What we should see is kind of the NAS drive which is in front of it. We should see the other robot that's just next to it there. We should perhaps see my side, which may move a little bit, but only a little bit, and we should see everything else is stationary. So this doesn't look right to me. We can also see that it says it's waiting for a packet of data. So it was at this point when I checked the Pico, put my finger on the top there, and I felt that it was absolutely red hot. And what had happened was I'd put the power in the way that I expected. So I put the red 5 volts into the red cable and the black ground into the dark cable, and that was actually incorrect because the wiring spec says it's the other way around, even though red is universally 5 volts or voltage, black is universally ground. So at that point I think I might have damaged, or I definitely did damage my LiDAR, and I can't get accurate data from it. So rather than this just being a garbage show with not very much to show for it, I thought let's talk through how we go about troubleshooting such an issue. So what I'm going to do, I'm going to load up my next one, which is test alive. So I've written some code here, and what this is going to do is it's basically going to test that we're getting the right data from our LiDAR. So let's see what it says there. So it's found the header, it's found all the headers. So the fact that it's found the headers means that the LiDAR is alive and is sending packets. Are those packets correct? So what we need to then check is to see, is this running correctly? So I'm going to run this spin test. Now look at this. So it's captured packets with the timestamps, and the timestamps, interestingly, this one jumps down here to 3950, which is very weird. And then we should have the packets coming in at a pretty universal rate. And what I see every single time is packets 4 and 5. I've got these really long times coming back, and that isn't correct. They should all be the same. So if I run that again, you see packet 6 is incorrect there. Packet 6 again has got a really long time. So the average time between packets is over 3,000 microseconds. So the motor speed is abnormal. It might be stuck or faulty, and I suspect that the motor took all that voltage when it was incorrectly wired, and it might have damaged the speed that it's running around. So we're getting all kind of garbage answers coming back there. If the motor's not spinning in a consistent way, we're not going to get accurate readings from our LiDAR. We can then do a pro level diagnostic where it actually looks at the actual packets coming through, and we can see there that again, the motor RPM is abnormal, might be too slow or too fast. And we can see there the actual angle of each of the readings that's coming through, and that the timestamps are irregular. I mean, they're very, very close there, but then we get these where it kind of drifts, and we've got that very large one, and that shouldn't happen at all. So I'm going to have to order another one of these, and then really check when I put the power in that it's actually the correct way round. So let me see what else we've got on here. So that was the spin test, the alive test, and the diagnostics. So the next thing I did, I loaded up ChatGPT, and I created a debug program which would, if I just bring this down, so this debug program is going to help me tweak a couple of things. We're going to read in some packets, and we're going to verify those packets, and then we're going to check is the distance valid or not. We shouldn't get any impossible distances from this LiDAR. So given that I'm in a 4 meter by 3 meter-ish space, you can see there some of the distances that are coming through. These look pretty alright, but then every now and again we get some which says bad, and we get impossibly large distances. So let me just wait for it to do one of those. So let's just back up there. Let's see what we have. Here we go. So these 56,576 millimeters. So that's like 56 meters, is it? That's impossible. That shouldn't happen. So that tells me, and it's got quite a high confidence of that as well, which is incorrect. So I tried all different combinations of, well, maybe the packets are not the right size. So I created a debug program that would actually spit out the packets of data. Let's see if I can find that one, which is it the test one? I think it's one of my debug ones. Let me just try debug 2. There we go. So I've spat out some data, and you can cut and paste that into ChatGPT and say, debug this. Is this data look valid for an LD06? And it can actually tell you. So again, always starts with the right packets of data. We've got that hex 54 and 2C, and if we check through here, you'll probably see another 54 and 2C. There's another one just there, for example. We can count the number of bytes between those and see, you know, is that like a valid block of data? And the number of packets are correct, so that the microcontroller that's on the board is working correctly. It's probably just the motor that's driving the LiDAR around that's not working correctly. So let's actually open up and see how this works inside, shall we? So I'm going to go over to the main camera here. I'll zoom in a little bit so we can see what this looks like inside. Now, I did check, it's totally safe for me to open this up. You probably don't want to do this on one that you're using, because if any fluff dust gets in there, that can actually get onto the LiDAR and affect the readings. But given this one is damaged, we can take the opportunity to look in this and see how this works. So what I will do is I will stop this. I'll just power off the LiDAR. Once the power stops, we can actually see what this looks like. So you can see there, there's these two little look like binoculars. So one is the laser that shines out, and the other one is actually the receiver that receives the light that's bounced off the object. And you can see that it basically just spins around, kind of infinitely spins around, taking readings, and because it knows exactly where the dead center is, it can accurately calculate, you know, what angle each of the readings is taken on. So if I power that back up again, you'll see that it spins around, and you can see that there's like a light there. When I look at this, the light is all the way around in like little segments. If I just pause that a second, you can see how that's kind of working. So it's kind of just one LED on there. There we go. There we go. It's happy again. It's working. But you really don't want to do that on one that is running fine. So let's just screw this back in so that it's in place. I thought you'd be interested to see how that works kind of behind the scenes. Oops, let's go screw this back in. It's an overhead shot of my hand there. We should go for that one there, for example. That might be a better shot. There we go. You can see how this should work. We've got that little arrow on the top there. That means that's facing forward. There's the pinouts. There's the very badly coloured cable. I don't know why they went with that colour combination. That really helped me damage my LiDAR unit. I've got a couple of cables there just going to a power supply. Ideally this would have a battery pack. You can see there those three screws hold in place the Kitronik motor driver board, and this is just sat on, you'll see there's a couple of screws. Essentially looks just like that. There's two posts. The original one I've measured it wrong, and the posts were kind of incorrectly spaced, so it wouldn't fit. That's why I had to print another one. But this took about 20 minutes to print. It's really, really quick. Okay, so we just go back over here to me for a second. One of the other things I wanted to sort of point out on there, when I create these LidarBot type chassis, in fact here's the prototype I did before I decided to use the LidarBot. That's got the two slots on for the LiDAR, and this was going to have the two motors underneath at the front, maybe a caster at the back. And you can see that I had the mounting holes for the Kitronik board, and I just decided let's go with the LidarBot instead, because the motors weren't going to work very well, and I thought if I need to start printing out these kind of fixed casters underneath there, it's probably just easier to use the LidarBot design. Now both of these use the same thickness, and this is something that I found works quite well. So that's 3mm thick, and when that's 3D printed, it makes it a really, really robust, putting quite a bit of force on there, and it's not for snapping. So you can see that it's very, very rigid, but also very, very lightweight. And I would say that's a perfect kind of thickness if you want to make robot platforms and that can print really quick. Because they're essentially flat with just a couple of protrusions on there, these print really, really quickly. So that might be like a 30 or 40 minute print. And it's got some infill. You might be able to see the infill pattern on there, perhaps just inside. If I put a light behind this, like with my phone, you might be able to see there's like a bit of a hexagonal. You can see that. You can't really see that at all, to be honest. But yeah, there's like a hexagonal pattern. I can see it as the light's coming through from the other cameras there, and the other lights there. So yes, that's a kind of prototype board that I made very, very quickly, and I switched to using the LidarBot with some custom holes on there as well. So they're all available from kesrobots.com. If you want to go over to kesrobots.com, let me load that up now, and I shall show you that working. Let's just do a new. There we go. If I go over to, just bring that down here. So you can see that if you're looking at this and it's like not the same week that I do this project, because these log entries change every week. You go to robots and then you find LidarBot, that it'll take you to the page all about this particular project. So you can see here's the video that you're watching now. A little bit of information about it, the cost of this particular build, so Pico, the LiDAR LD06, the Kitronik motor driver board, a couple of DC motors, some jumper wires and some screws. So it's quite a cheap project. You can see there are all the different parts that you can then download. There's the motor driver, the LiDAR and the wiring, and then there's some code available on GitHub. So once I've received the replacement part, I'll carry on working on this and hopefully get that nice radar thing working correctly. So there are all the different parts that you can download. So each of these are the little STL files. You can even view them in 3D straight on Kev's Robots. There we go. These are all designed to be very quick and very cheap to print as well. Cool. Let me jump back to my show notes. See if there's anything else I was going to cover off on there. Yeah, essentially just the technique for diagnosing the issues. That's one of the things I wanted to cover off on there, because this does happen in robotics. You do get issues where things don't kind of go to plan, and you have to figure out how to figure out what the actual issue is there. So I'm just going to check on that over there. So the way that I diagnosed this was, first of all, have we got the wiring correct? So does the UART get any data back from the LiDAR? And then we checked what the data was that was coming back. So are the headers looking correct? Could we see that 54.2C, for example? We could see that, so that means that the microcontroller on the LiDAR is at least sending what it thinks is valid data. We could then inspect the packets of data to see, do they look valid? So are the ranges of things that they're sending back within what we expect? So are the distances reasonable distances for the environment that's in, or are they impossible distances? And then we could check things like the speed at which they're coming back. Are they what we would expect within the range of values? So we could then narrow down where the issue potentially could be. So the fact that I was getting good data back from the LiDAR, but then the actual packets of data had impossible distances on them, that tells me either I'm not reading in the data correctly. So I went through a few iterations of checking big endian and little endian for number encoding. I tried quite a few other different things like the length of packets. It does provide a data packet that tells you how many packets of data are in this particular reading. You can use that, or you can just process the packets as they come through, because it tells you the start and the end angle for each of them. So you can basically just check, is that correct anyway? So went through all those different steps, and essentially what I found is it must be damaged when the polarity was the wrong way around, and it didn't totally damage the LiDAR, but the data that you get back isn't workable. So really disappointed with that, but hey. So if you want to make yourself one of these gamepad remote controls. You can do that by ordering one of these PCBs from kevsrobots.com. We have quite a few of those still left in stock. And we also have some of the Robot Maker Almanacs, and we also have the Maker Notes as well. So the Robot Maker's Almanac has all the GPIO pins, pinouts. It has all the dimensions and things of common parts. And we also have the Maker Notes, which are basically just blank notebooks. There's little dots on so you can draw circuit boards and things like that. They're all pocket sized with these nice rounded corners. So they kind of play very nicely together with each other. So definitely check out those on kevsrobots.com. It also helps the show. And if you've not joined our Discord server, you're definitely missing out. You would definitely want to head over to kevsrobots.com/discord and get yourself a sign-up link. It's completely free, and you can share pictures of projects you're working on, ask other people for help, and you'll know you're in a good community of people who are all very like-minded. And if you want to follow me on social media, I'm on all the social medias. So I'm on Threads at Kev McAleer at threads.net, on TikTok at Kev McAleer6, I'm on Instagram at Kev McAleer, I'm on X at KevsMac. I'm on Mastodon at kevsmac at mastodon.social, and I'm also on kevsmac at bsky.social as well, so that's Blue Sky. So definitely want to follow me on those. Say hi if you follow me. I'd love to know what you're working on, and if you're working on any of the projects that I've made, you're inspired by them, I also like to know about that as well, because why not? And if you want to join me and get your name in the end credits, you can do that by going to kevsrobots.com/coffee. All the instructions are on there, and you can do that. So let's give a shout out to the people who've done that this past week or so. So let's have a look. So we had somebody buy me 3 coffees. Thank you so much for that. I really do appreciate that. We'd had a bit of a dry spell where nobody bought me a coffee for a while. And we've got a couple of members on the Buy Me a Coffee side. So we've got Silicon Fiber, Marie TKD, we've got Andrew, Jeff, DN Corty, Marlene, and we have Tom. Thank you for being members over there. And on the YouTube side, Pierre Eves has recently joined this past week. We've also got Charlie White, I think joined last week. We've got Oxford39, Bert, Marie, we've got Michael, Steve, Ford, Bello, Little Back. We have Paul, Johnny, Stephen, John Paul, Cassie, Tinkering Rocks, Johnny, and of course we have Tom. So thank you so much for supporting the channel. It means so much to me that you continue to do that. If I just go back to those last slides, the little spinny logo thing there tells me it's time that YouTube will be recommending over here one of the videos for my over 400, I think it's 420-ish videos I've uploaded now to YouTube. So definitely check out one of those. It's picked it out just for you, one that'll be right up your street. So binging that helps also grow the channel, so I really do appreciate that. And it's at this point in the video I'll say thank you so much for watching, and I shall see you next time.